Great. Welcome back to the last day of the BNASC workshop. Um, so the first speaker of this session is Naomi Nickerson from PsiQuantum. She's going to tell us about interleaving architectures for photonic fault-tolerant quantum computing.
Great. Thanks very much, Steve. And thanks for giving me the chance to talk. It would obviously be much nicer to be seeing you all in person, but at least we still get to talk science. So I'm going to talk about a particular kind of architecture for fault-tolerant quantum computing using photonics. And this is, move my slides. So this is work which is going to be appearing on the archive soon, and I want to just take a moment to give credit to the whole quantum architecture team at PsiQuantum, and in particular, these are the people who have worked the most on this particular topic. And this is really a talk about fiber. So this is a picture of an optical fiber, and I'll say a bunch more about this over the course of the talk. But this is really one of the key reasons. The fact that you can take photons and route them from one place to another is one of the things about photonic architecture that gives it a whole lot of flexibility. And this is something we talk about a lot with photonic architectures, how you're not constrained to 2D and how you can wire things up in different ways. And I want to talk about just one example of how we can do that. And this example is something that is about how we count resources in an architecture for fault-tolerant quantum computing. So this is two pictures of two ways that you can think about doing fault tolerance, of making a logical qubit. These are obviously very schematic kind of figures. So on the right-hand side, this is something that should be very familiar. So we have an array of matter-based qubits, and we use those to prepare a surface code, which we then do operations on over many time steps. And we can use that to then create a fault-tolerant channel that we can use to do logic. And then on the left-hand side is how we can think about that with a photonic architecture. So instead of matter qubits, we now have some physical piece of hardware that is an array of photonic resource state generators. And every time step, those produce some small entangled states that we can then stitch together to make a three-dimensional cluster state that has all the same properties of being a fault-tolerant channel, and we can then use to do computation in a very similar way. And obviously, I've drawn these two pictures in such a way that you can see that they look extremely similar. And I'll say a bit more about this photonic case and kind of how that stitching together of those states works a little later. But the question that we want to ask now is, if we're counting resources, if we're asking the question of how much hardware do I need to do a particular computation, how do I compare between these two cases? So the first thing to say is that if I'm looking at a photonic resource state, so one little piece of entanglement that's going to go in to create one site of this cluster state, I should really be thinking about that as being like one matter qubit in one single time step. So this is a state that gets used once and then it disappears, it doesn't get reused. So it's really like one instant in time. And then I can look at the hardware, and now I can think about a physical photonic resource state generator, so something that's producing many copies of this state, as being sort of equivalent to one matter qubit that is over all time steps, so a physical matter qubit that sits there and you can use multiple times. And this is kind of the story that you get from the picture that I just showed you. But the story, the thing that I want to convince you of over the course of this talk is that if I add that fiber, so if I throw that fiber into the mix in my photonic architecture, that can really completely change the story about how I'm counting resources. So in fact, if I have a single photonic resource state generator and I add this fiber, I can actually now think of that system as being equivalent to many thousands of matter qubits rather than just this one. So this is the point that I want to get to by the end of the talk, of how we can make an architecture behave like this. So before I do that, I want to just go back to give a bit of an introduction on the basic operations that we need to do fault-tolerant quantum computing using linear optical operations, because it's maybe slightly less familiar to some people here. And I want to tell really the simplest version this story, just with the basic building blocks that we need to be able to piece something together. So the first building block is that we need to be able to generate resource states. So these resource states are small entangled states, small linear optical cluster states is what we usually think of. So I have a piece of hardware, which with some frequency is going to produce one of these little cluster states. So in this picture, we have the vertices, these dots are representing qubits, and each of those qubits has one photon in it. So there are different ways of encoding it, but you often think of a dual rail qubit where it's one photon in two modes representing a qubit. And the lines there are representing entangling bonds. And something that's worth saying is that for everything I'm going to talk about, I really don't care what is inside that resource state generator. You can think about a system which is entirely linear optical. So everything inside that box is also made of linear optics. But it really could be anything else that's allowing you to produce one of these linear optical cluster states with some frequency. So I could have a system which has trapped ions in it. I generate entanglement, and then I can map that to a photonic state. So that's my first building block. I have this resource state generation device. And then the second building block is linear optical fusion. So this is the operation that's going to allow me to create entanglement between two separate resource states. This is a kind of schematic figure of what that looks like. This device in the middle is a photonic circuit. So you can think of those lines as being waveguides that route the photons that I'm putting in from left to right. And so the fusion operation, you can see there are highlighted these two blue qubits. They get fed into this fusion box, and the fusion is a destructive entangling measurement that gets made on those two qubits, so that what comes out the other side is now the two states where the two blue qubits have disappeared, but I'm left with an entangling bond between those two states. Now, you probably are aware that linear optical fusion is an intrinsically probabilistic operation. So in fact, that doesn't actually succeed all of the time. But there are a whole bunch of tricks that you can use to increase the probability of success of those fusion operations. And for the times when it fails, those failures can be tolerated by quantum error correction, so they can be absorbed into the code. And so this is not going to be the topic of this talk, and so all of the pictures I'm going to show, I'm just going to show those bonds being present. And just know that the imperfections, those failures in the fusion, can be tolerated. So there's one final piece that I need, one final building block, and it's a different kind of a fusion. So not only do we need the ability to be able to take two resource states that were produced by different devices and fuse them together, we also want to be able to do a fusion between two resource states that were produced by the same physical device in two different time steps. So we call this a time-like fusion. And really the operation is almost exactly the same. The fusion operation is the same. But now we need to be able to take these two photons that exist in different time steps and move them together so that they arrive at that fusion at the same time. And all we need to do to achieve that is add in a delay line of a sort of one time step into one of those qubits, so that when they arrive at the fusion, they have become aligned in time. So this is a very small modification. It gives us what we call a time-like fusion. And the result is that we end up with this entangling bond that is connecting these two different states across different time steps. So with those three operations, we can piece those together to then generate large-scale entanglement. So here's a kind of schematic picture of how we can piece those different steps together. We can start off with, rather than just one resource state generator, we have some array of those resource state generators in a piece of physical hardware. In every time step, those are going to produce an array of resource states. So that's what you can see in the first layer here, that are kind of arranged in a layer. We can then perform these space-like fusions to fuse all of these states with their neighbors on every side. And that results in this thing in the second layer, which is a 2D layer of entanglement. And then finally, we want to take multiple of those layers and perform time-like fusions that connect the layers together so that we end up with this three-dimensional structure of entanglement. And just to look a little bit closer at the actual hardware that's needed to get to that point with this example. So we have this array of resource state generators, and those things are spitting out these resource states into a bunch of photonic modes that are then going into these 3 different fusions. So we can look at that thing as a little photonic circuit, which has these 3 different fusion operations. So we have 2 of these space-like fusions where the photons are connecting with photons from neighboring sites and going into these fusion operations to get connected into these layers. And then at the bottom, you see this time-like fusion. So there we have 2 photons that are coming from the same resource state generator going into this time-like fusion, and that's connecting one resource state with the one at the next time step, and so on. So I guess the important thing to flag about this piece of physical hardware that we can then tile out to create a logical qubit is that the architecture is constant depth. So what I mean by that is if we need to make a bigger logical qubit or to increase the size of the computation, what is happening locally doesn't change. So a photon is produced in this resource state generator and it travels to the fusion, at which point it dies. And that world line does not change when I have to scale up the size of the computation. Obviously, this is a pretty essential feature for a photonic architecture. So at this point, we have this 3D block of entanglement. And this is a resource for universal quantum computation that we can use to do fault tolerance. And I'm not going to say more in detail about how we use that thing to do logic gates and so on. Very conveniently, Ben Brown gave a nice overview of that a little earlier during this conference. And so I'll just say that, you know, once we have this, we can use it. And the other thing that's worth mentioning is that the example that I gave with this is just a 3D cubic structure. That's an example which is just easy to describe what's going on. And there are many other structures of entanglement that you might choose to make in a similar way. And probably what you would choose to be making is one which is directly fault tolerant. So one of these fault tolerant cluster states that Ben talked about, or the one in this picture here, which is the one that's kind of equivalent to the square surface code over time that was first introduced by Rausendorf, Bravi, and Harrington. But everything that I'm going to go on to say, the message doesn't change if I'm talking about a different structure of entanglement. So I'm sticking with the simplest possible example. Okay, so this was the introduction. It's actually pretty simple. So we have these small number of building blocks. And I now want to go on to talk about this idea of interleaving and how we can use the same building blocks with a delay in a bit of a different way. So this is just a picture of exactly what I was just telling you about, except just to keep everyone on their toes, I've rotated it by 90 degrees. So now we have a piece of hardware at the bottom that's producing these layers of entangled cluster state over different steps in time. And then we're doing these time-like fusions now in the vertical direction between these different layers. And I now want you to imagine a very small variation on this scheme, where instead of doing these fusions between successive layers, I'm going to do fusions between layers that are separated by 2 time steps. So something like this. So I can imagine my layers being separated into these two kinds of different colors. And I'm going to do these time-like fusions now between the layer generated at time 0 and 2 and 2 and 4, and the layer at time 1 and 3 and 3 and 5, but not between layers that are next to each other. And what I need to do this, if I can look at the hardware, what you'll see is that almost everything is exactly the same as it was before. So I'm still creating the layers, I'm still doing the exact same fusions within the layers. And the only thing that's changed actually is that with this time-like fusion, I'm now increasing the delay from 1 to 2. So it's really a very minimal change in the hardware, which is just to double the length of one of the delay lines. And you can kind of see from this picture, the effect of this is that I've got all these these entangling connections now between the layers, but I've got no entanglement that's between red and blue. And so I can imagine sort of separating these two things out, and what I'm left with is two copies of the same state that I was preparing in the beginning, but two completely separate copies that are not entangled to each other. So the result is that I've used this one piece of hardware to create two copies of the same state that are sort of interleaved together in time. And so the gain that we've got here is we're using the exact same piece of hardware, so maybe a piece of hardware that I could have thought of as producing one logical qubit, and I'm now using it to produce two logical qubits. And the cost is that I'm doing it at half the speed that I was before. And so obviously this scheme can be generalized by increasing the length of that delay further. So rather than having a length 2 delay, I could have a length 3 delay. And now I end up creating 3 copies of that state that are interleaved together. But I guess one thing which is kind of worth flagging about the game that we're playing here by adding these delay lines is that in each time step, I don't get to choose a different connection. I'm not getting to choose in every time step which layer I'm going to connect this one to. It's something which is fixed, that delay line is fixed. And so it's kind of a critical part of the scheme that I'm doing something to every layer which is the same, and the operations I'm doing always stay the same. So you can kind of see what's happening here, which is this is basically making a trade-off between space and time. Instead of creating 3 physical logical qubits, instead I have the option, by employing this interleaving scheme, of creating one sort of physical piece of hardware and running it for 3 times as long as an alternative. So this is a way of giving us flexibility with how we're choosing to distribute resources between space and time. So I guess what I talked about so far is really just focused on creating a state. It's about a quantum memory using a logical qubit as a memory. But the other thing we need to—
Naomi, can I just ask you a question, if that's okay? When you say that there's a trade-off between space and time, when you do this thing where you use a delay line that's 2 or 3 steps, does that mean that 4 of the time slices have to be alive, in quotes, at the same time? It's like you have to have some number of layers that exist physically at any one time, and then old layers get measured out, right?
Yeah, so what you can think of is that all of these, so there will be 3 layers that are sort of hanging out in the delay line at once. So, I mean, you can think of as sort of 2 of them are hanging out in the delay line, whilst the 3rd is arriving at the fusion to meet the new copy which has just been created. So yeah, you can think of all of the ones that are waiting. Their photons are just sitting in this delay line, kind of stacked in time.
Okay.
Okay, so yeah, and that's what you need to do in memory. You have all these things sort of stacked in time in the delay. But I mean, that actually kind of leads on well into this question, which is, to do logic, you need to be able to manipulate the qubits. And it's maybe not obvious immediately how you're going to do that, because you have them sort of hanging out, waiting in the fiber, or waiting in your delay line. And you want to be able to choose how you interact with them to be able to do logic. But it turns out that's actually pretty straightforward to do in this kind of a picture. And we can do it just by adding some additional connectivity in time, so doing some additional time-like fusion operations just at the boundary of these qubits between the different layers. So in this picture, we imagine we're doing all the same time-like fusions that connect these layers of the same color, but then we're additionally going to add fusion operations that are connecting these 2 blue layers together just at the boundary. And if you look at the sort of unfolded picture of that setting, you can kind of see what's going on. That is, we have the red qubit, which is untouched, and then we have the 2 blue things which have been stitched together at one of their boundaries. And so this is basically allowing us to do a lattice surgery type operation by connecting these two things together. And so we can, stitch them together and then we can split them, and that allows us, if we take that in conjunction with single qubit operations, which are left unchanged in this picture, that allows us to do all of the logic we need for computation. So I guess just to slightly change the way of thinking about this, there's one other thing I want to say about this framework of thinking about layers and fusing them together in different ways, which is, aside from being able to trade off between space and time, this way of thinking actually also adds a whole bunch of flexibility into how we start to think about the topology of the code that we're creating. Because now we're thinking about these layers and fusing them together in different ways. We no longer need to think about a code which is really just created in one 2D layer, but we can imagine taking this, so any sort of two-dimensional code, and folding it so that we actually create it across multiple time steps. And by taking codes and folding them, you can, sorry, did someone have a question?
Yeah, finish your thought and then I'll.
Okay, I'll finish this slide and then I'll ask you. So yeah, you can imagine folding these things in time so that you bring boundaries together to create, say, a cylinder as an example. If I create this across 2 time steps, my long-range connection that I would have needed to kind of stitch the other boundaries together becomes in the same location in space and just separated by 1 time step. So things that were non-local become local in space and time by modifying topology in this way. Yeah. What was the question?
Yeah, so Narayanan Rangaswamy has a question. I'll just read it out. Due to this interleaving, it seems to me that logical qubits cannot or are not produced on the fly. You want to know a priori how many logical qubits are needed. And the motivation for interleaving rather than coupling consecutive layers is to make sure that all the logical qubits are produced simultaneously. Is this correct?
So, okay, so I guess the way I'm describing it is that I have one logical qubit and I'm multiplying it up to create some larger number of qubits. But you could obviously imagine having a device which was, say, I always used it to create 10 logical qubits, and then I had another space where I also created 10 logical qubits. So I don't need to think about this as being the entire system, and I program it in different ways. There are different ways of thinking about scaling that up.
Okay, thanks. I think that answers it.
That answers the question. Okay. So I guess now I want to just change tack a bit and talk about hardware and some more realistic considerations, because this is, I guess, a kind of a bit of an abstract scheme, and the requirement is that we throw in these additional delay lines. So the thing you want to know is, obviously, is that a reasonable, realistic thing to do? And this is where the optical fiber comes in, because optical fiber is really an incredible piece of technology that I've come to appreciate much more in recent times. And the loss of an optical fiber is 4% per kilometer. So that means I can put a single photon into that optical fiber, and 1 kilometer later, there's still a 96% chance that that photon arrives. And this is it's already been a very world-changing technology. It happened in the 70s, where there was this big step change in the quality of optical fibers. And they really went in the space of a few years from being about 20% loss per meter, that was in the 60s, to midway through the 70s, they were at 5% per kilometer. And they basically haven't changed since then. And that massive change, it won some people a Nobel Prize for the theory work that went into getting there, which was all about removing the imperfections in the optical fiber. And it's obviously completely changed the way we communicate. And it's because the loss that these things experience is so incredibly low. And so from the perspective of the fiber itself, it really is very positive for being able to have these very long delay lines. But it's not the only thing you need to think about. There are some other considerations as well. So The first really important thing is that to be able to make use of that very high quality fiber, you have to be working with telecoms wavelength photons. Those are obviously the bandwidth that those fibers are designed for, and that's what you need to be able to get that really good loss property. You also need to be able to have very low loss coupling into the fiber, because it's no good having this really good fiber if you're losing a whole bunch getting in and out. The good news there is that there's actually already been reported these pretty low loss couplings into fiber in the literature, so around 4%, and I think there's also a bunch of scope to push those numbers down. And finally, you also need low dispersion in the fiber. So dispersion is something that can lead to Pauli errors if you have it, so we also want that to be low. So you can look at all these numbers, and I think that the conclusion is, well, I can't just take fiber and super glue it to an optical chip and expect that that's going to work. But yeah, the numbers are actually pretty promising, and it seems like this is something that is actually feasible. So if we take this fiber and we say that this loss rate of 4% per kilometer is like some estimate of the maximum that we could tolerate, so we're going to take a kilometer of fiber as our delay line. It takes a photon about 5 microseconds to travel the length of that fiber. And if we have this resource state generator that's producing states at a rep rate of a gigahertz, that means that we can fit 5,000 time bins into that fiber. So our 1 kilometer long fiber is going to give us 5,000 time bins. So I guess just to say a bit more about these space-time trade-offs. So if anyone here who has worked on photonic architectures or some kinds of photonic quantum computing will know that the idea of trading off between space and time with photons is not a new one. And time multiplexing with photons is an idea that has been around for a long time. But there are some really important distinctions between this scheme of interleaving that I'm talking about now from other kinds of time multiplexing. And that is basically all because this is a time-space trade-off that is happening at the level of the logical qubit rather than at the much lower level of maybe multiplexing single photon sources. And that leads to a bunch of properties that are really important for making it a practical scheme. So the first is that it means you need actually a very small number of delay lines. So in the scheme I've described so far, you just need this one delay line per qubit that's going into the code. If you do it at a lower level, you're going to need a much larger number of delay lines. Then also the loss of that delay line only ends up getting applied to the qubits that are sort of at the final level, they're already in the code. And again, if you are applying the loss of the delay lines to something that's happening earlier on in the protocol, then the loss can have a bigger impact. And so it's definitely preferable to be doing this at a later point as possible. And then finally, and this is also a really important one, it doesn't require any switching. So the circuits that I was showing you, you'll see that I don't need to be flipping a switch to change what delay the photons are going into, at least in the bulk. It's always the same circuit. And so the scheme is really not adding the need to do any complicated switching, and I'm still getting the advantage of this time-space trade-off. So I guess, yeah, for people here who think about algorithms and compiling, everyone should always be concerned when you hear about trading off between space and time, because you need a lot of gates to do something useful with a quantum computer. And so you do have to be cautious, and ultimately there'll be some trade-off between how far you want to push this. But I think it's pretty reasonable to think that with first generation quantum computers, space is going to be a much more expensive resource than time, and we're probably going to be willing to wait twice as long to get the answer to a computation rather than building a device which is twice as large. So exactly where in that trade-off you want to end up is probably an open question, but you can kind of look at the numbers and see that you still end up with things that are sort of reasonable looking if you plug in some numbers to the example. Okay, so
just keep an eye on the time. You have about 5 minutes left.
Okay, So let's try and ask the question of how far we can push this then, because we've looked at this optical fiber. We can say, well, we can fit 5,000 time-ins into that fiber. And the problem is that this scheme that I've described so far, we take one logical qubit and we use this delay to multiply up the amount of space that we have there. But something which is maybe non-ideal about this is that perhaps I don't want to build a quantum computer that has 5,000 logical qubits. I'd really like a way of using that factor of 5,000 that I can get to reduce the footprint even more, rather than continuing to multiply up the number of logical qubits that I have. And so, and this is the last thing I want to talk about, which is this is a variation of this scheme. So rather than starting with this whole logical qubit, I can instead start with just a single resource state generator and use it to create a patch. So I can use it to create a layer one site at a time. So now you get to see this nice animation. And so this is really in the spirit of sort of 3D printing the cluster state. So rather than producing it a whole layer at a time, I can produce this one state at a time and then do the fusions that I need to connect this together into a single cluster state. So there are a bunch of different kind of considerations that come here, and I'm not going to go through this in detail, but the question that you really care about in this setting is, well, how does this affect the number of delays that I need, the number of different delays, and how does it affect the switching? And so it turns out, this is very dependent on exactly the geometry you're using and exactly the code, but for this example, you can create this structure if you choose the ordering of the sites that you're creating in such a way that the delays that you need are only 3. So I'm only going to end up needing a delay of length 1, and that's to connect anything which is connected in the x direction. In the y direction, all the sites are separated by a length of L, so 4 in this case, which is the size of this patch that I'm making. And then the delay that is separating the layers from each other is always L squared. So I can look at the back at the piece of hardware that I need to create this system. And on the left is this picture that I started with, where I have my photonic state going into these 3 different fusions, where 2 of them are space-like and 1 is time-like. And with this scheme, which we call rastering, this sort of 3D printing idea, you're taking the state and you're routing it into 3 time-like fusions. So now I have these 3 fusions, all of which are delayed by different amounts. And again, the kind of remarkable thing about the system is that, firstly, you only need these 3 delay lines to be able to create all of the different entangling operations you need. And you also don't need to do any switching. So the resource state is always going into the exact same configuration. And so if we take this system and we kind of push it to this extreme, and we imagine having our longest delay line, this L squared delay line of having 5,000 time bins, then that means we can take this one resource state generator and use it to create a patch that's size 70 by 70. So pretty decent logical qubit from one resource state generator. And okay, so this is basically the final thing I want to say, which is just to zoom out and think about what we're getting from this optical fiber. So fiber is basically an extremely good quantum memory. It can store thousands of photons and it can store them extremely well. But it's not super obvious at first glance how you can use that to be useful in doing quantum computing, because it's not a very flexible quantum memory. I put a photon in and the photon comes out at some fixed time later, and I don't get to choose how I interact with it at any time before then. And so if I have 2 different photons that are in this fiber, I can't just choose to make them interact. So it's really a very restrictive system. And so the surprising thing about this scheme of interleaving and about rastering is that using these fibers, and actually using only a very small number of these fibers as a photonic memory, you can get all of the interactions you need to be able to make the kind of 3-dimensional cluster state that you need for fault tolerance, and to be able to get all of the operations you need to do logic. And that's really just saying something about the very specific scheme and the very specific kind of structure of entangling operations the type of connections that you need to be able to do fault tolerance and fault tolerant logic. So yeah, just to sum up, this is the bottom line, which is that resource counting looks very different with photonics, and that's because of the existence of photonic delay lines and in particular optical fibers, which mean that it's possible to store tons of photons, and in fact whole logical qubits in delay lines to multiply up the amount of quantum space that we're getting access to from a single state generator. And that gives us a bunch of options. So it means that we have this possibility of freely trading off between space and time. And what it takes is actually very limited changes to the hardware. You still have the option of doing logic. And then the thing which I think is more open-ended and opens a bunch of really interesting questions is that when you start to think about creating states in this way, with these layers and fusing them together in different ways, it plays very nicely with the ideas of modifying topology and starting to look at things that are beyond strictly 2D. So periodic boundary conditions or things with different structures. And I think, yeah, it makes it very kind of exciting and interesting to me to see all the different work that's going on with hyperbolic codes or LDPC codes, because those actually become a practical prospect when we're thinking about this kind of architecture and using photonics, where we have these different routes to connecting things up and building these structures. So I'll leave it there. Thanks very much, and yeah, happy to take some questions.
Thank you, Naomi. We have some questions. Daniel Miller says, thank you for the nice and interesting talk. What is the analog of circuit depth for photonic measurement-based quantum computation? And does interleaving imply also a trade-off for circuit depth and number of interleaving levels?
So I guess there are two aspects to circuit depth. I'm not sure which one you're asking about. So there's a physical circuit depth of what is happening to your physical qubits before they get measured out. And so the analogous thing there is to look at the lifetime of a photon. And so this is where we can look at a circuit and we see that photon is created, it goes through some operations, and then it gets measured out. And that's always a fixed and short timeline. So that's very similar than in a matter architecture where I'm making repeated stabilizer measurements that kind of project out on my qubits and then I measure them out. And then if the question is about the circuit depth of the logical computation, so yeah, the trade-off there is maybe not the obvious one. If I'm using an additional delay line to do interleaving to kind of multiply up the number of logical qubits I have, that's not then restricting or putting a cap that is a bunch of is the same factor shorter on the length of computation I can run, but the computation is going to take longer. So this is operating in a regime where you are below threshold, and so I can increase, I can always increase the footprint a bit to get into a sufficiently below threshold regime, but it's not a direct trade-off where if I interleave by a factor of 5, then I can compute for a factor of 5 less. I still get the same amount of computational time.
Okay.
The only possible cost is that you're adding a little bit of extra loss to multiply it up, and so you have a small amount extra error, and so I'm operating perhaps a slight bit closer to the threshold. So there's maybe some small modification, but it's not a direct one.
Yeah, thank you. That was my question.
We have 2 other questions, but I think maybe we can answer them in the Slack channel in the interest of time. Is that okay, Naomi?
Yeah, absolutely.
Okay. Or you may be able to, as a panelist, answer them directly in the Q&A. I'm not sure if you can see them.